Okay, good morning, all participants as well as speakers, Jiraya and all representative from 5 countries of the ASEAN member states. Thank you so much for coming to this Cspf online lecture for non-labs countries today and Thursday, 10 February 2022. We will have the session today. We'll divide it into 2 sessions. The first sessions will run around 60 minutes, so for an hour, and then we will have a digital break later on for 15 minutes. So please stand ready. And then we will have Q&A sessions on the last after the second presentation sessions. So if you have any questions, please feel free to write down your questions on the chat box, or if you want to raise your questions directly, please raise your hands during the Q&A sessions. And I would like to welcome all of the partners here, Jiraya, and all ACE colleague and all AMS representative as well. My name is Amira Bolkes, and I will be assisting your today's online lectures. And to begin with, I would like to invite Dr. Andi Tirta for giving an opening remarks, short opening remarks for today's online lecturing. So without further ado, Dr. Andi Tirta, please.
Yeah, thank you so much, Amira. Good morning, all excellencies, Datuk Sir Madam, and all colleagues from JRIA, from ACE, and also from IMS. Today, we are so much happy to have all of you, of course, during this challenging time, this pandemic, that perhaps if there is no pandemic, we could meet each other in the one of country is in IMS. As you know that we are in the ASEAN Center for Energy. We are today holding the implementation of the project, what we call as the promotions of higher efficiency air conditioners in ASEAN through harmonization of standard and strengthening of market verification and enforcement capability in this phase 1, or what we call easily CSPF project. The project is funded by the ASEAN-Japan Integration Fund, or JAIF 2.0. And as you know that as a part of capacity building program of this project, ACE, currently we are conducting a round-robin tests in several laboratories in IMS. We have in Indonesia, Malaysia, Philippines, and also Thailand and Vietnam, and all in laboratories still ongoing. And of course, during the RRT test, all the laboratories are previously joined the online training to prepare and also to know more about the CSPF itself. And to ensure delivering CSPF capacity building to all AMS, today we would like to conduct the CSPF online lecture for the AMS without national AC testing laboratories. Of course, in this regard, we are pleased to have all of you participants from the technical working group members from Brunei Darussalam, from Cambodia, from Laos, PDR, Myanmar, and Singapore today even, yeah. Today we are starting around 9 until 12 today for around 3 hours. Thank you, Amira, for conducting these activities. And of course, this lecture will be delivered by the Japan Refrigerations and Air Conditioning Industry Associations, or we call as the JRIA, which aims to provide a detailed explanation about the CSPF ISO 16358 evaluations method as the harmonized standard in the ASEAN region for AMS that without national AC testing facility. We believe that by this online lecturing, better understanding about this standard the participant will get this understanding easily through this lecture. And as you know that last year, this ISO, this standard is already adopted by the ministerial meeting and stated on the joint ministerial meeting on the last year. So of course, we hope you will get your better understanding. You could raise your questions if you have any. And of course, we are so much happy. Again, thank you so much for the support of the JRIA, IEA, and also JRTL to conduct this online meeting and also all the activities in the CSPF projects. Back to you, Amira. Thank you so much. Good morning and stay healthy and stay healthy for everybody. Yeah, back to you, Amira. Good morning.
Thank you so much, Dr. Andy, for the warm welcoming remarks. Now I would like to invite Mr. Kasahara-san as the General Manager of the International Affairs of Jiraiya. And without further ado, Mr. Kasahara-san.
Yes, good morning, everyone. This is Hideaki Kasahara from Jiraiya, from Tokyo. I'm General Manager of International Affairs Department in Jiraiya. Oh, thank you. Yes. First of all, I'd like to thank ASEAN Center for Energy for giving us an opportunity to share our knowledge on seasonal efficiency, Cspf, with participants today. So please give me a time to introduce ourselves, Jiraiya. As you can see on the slide, yes, and Jiraiya is an abbreviation of the Japan Refrigeration and Air Conditioning Industry Association. So we are an association of HVAC and R manufacturers in Japan, established in 1949. So major Japanese and world-leading brands of refrigeration and air conditioners are our member companies. So after my speech, our technical expert, Mr. Minetoshi Izushi, explains about the seasonal efficiency of air conditioners based on ISO standard 16358. You know everything, he knows everything about the standard because he is a man who drafted the standard at ISO Technical Committee TC 86 SC6 in 2007. So since it was published in 2013, Jiraiya has been promoting the ISO standard to many countries. One particular example is a project named as IES Innotech, supported by METI, Ministry of Economy, Trade and Industry of Japan. So the project was to support adoption of ISO 16358 standard and installation in Indonesia, Malaysia, the Philippines, Singapore, Thailand, and Vietnam. The current harmonized MEPS in ASEAN, which is CSPF 3.08, has been delivered as a result of the activity. Okay. So this is all my opening speech. Thank you very much for your attention. And please welcome Mr. Izushi for his presentation. Thank you.
Thank you so much, Hideaki Kasahara-san, for the opening and introductions. What is Jiraiya to our colleague here at ASEAN member states. Now, before we begin our sessions, I would like to invite everyone to turn on your camera because we are going to take a group photo. So I would encourage everyone to turn on their cameras. And please smile to the cameras for now. Okay. We will wait for a couple of seconds. Thank you so much for opening your camera. We will wait for another 15 seconds. Perhaps our colleague from Singapore would join. Okay. Okay. Okay, then let me take a pictures. In 3, 2, 1, smile to the camera, everyone. Okay, please stand one more time. In 3, 2, 1, everyone smile. Okay, thank you so much for your kind attentions. Now we will move on to our next agenda, which is the presentations that will be led by Minetoshi Izushi-san to present the first session. So without further ado, I would like to invite Minetoshi Izushi-san to the floor. Thank you.
Good morning. My name is Minetoshi Izushi from JRAIA. Thank you for giving us a chance of presentation today. The presentation is about guidance to seasonal efficiency CSPF for ASEAN and labeling. Next, please. Okay. These are contents. Basic explanation about CSPF from section 2 to section 5 is not so different from those we explained in the kickoff meeting of work package 1 and 2 in this CSPF project. But many examples of calculation are added this time for your better understanding. Section 6 for general procedure to make labeling table is also added this time, which will be helpful for each country to prepare effective regulation to practically promote higher efficiency of air conditioners in the market. We'll have a short break between section 4 and section 5. Next, please. This is introduction. Currently, global warming issue is accelerating to promote energy saving of air conditioners because 70 to 80% of CO2 emission is due to use of electricity. Also, number of air conditioners is continuously increasing in ASEAN. CSPF and other seasonal efficiencies are being adopted in many countries because those can evaluate the product efficiency and annual energy consumption correctly. In order to promote energy saving, amount of annual energy consumption must be correctly evaluated. ASEAN is going to select CSPF as a harmonized evaluation method for MEPS and labeling. General procedure for calculation and labeling are shown here. Next, please. This page shows a definition of EER, WEER, and CSPF. Energy efficiency ratio, EER, is cooling capacity divided by power input. EER is applicable to any test condition, but rated EER of products is defined in standard full capacity test at 35 degrees C outdoor temperature. Weighted EER, WEER, or weighted COP, WCOP, is a weighted average of full capacity EER and half capacity EER tested at 35 degrees C. Cooling seasonal performance factor CSPF is total cooling load divided by total power consumption. Both total load and total power consumption are sum for all operating temperatures during the cooling season. CSPF is a kind of weighted average of EER during the cooling season. Next, please. This page shows conventional EER and CSPF for fixed capacity unit. The left figures show a tested ER at 35 degrees C and typical operating hours of air conditioners at each outdoor temperature. In this figure, conventional ER is the efficiency at only 35 degrees C and cannot evaluate efficiencies at other lower temperatures in majority zone. The right figures show calculated full and actual ER and operating hours at each outdoor temperature. When the outdoor temperature decreases from 35 degrees C, cooling load decreases because entering heat from outdoor side becomes less. On the other hand, operating full capacity and ER increase because it becomes easier for the air conditioner to carry heat from indoor to outdoor side. Because the fixed capacity unit cannot change capacity to meet the smaller load, the unit enters on-off operation. Actual ER decreases from full ER by on-off, but still slightly increases when outdoor temperature decreases. Cspf is a kind of weighted average of actual ER for all operating temperatures. Cspf can evaluate higher efficiency of air conditioners at lower outdoor temperatures. Next, please. This page shows weighted ER and Cspf for inverter or variable capacity unit. The left figures show tested full and half capacity ER at 35 degrees C and calculated weighted ER and operating hours at each outdoor temperature, which is same as the previous page. In this figure, WER is a weighted average of full and half capacity ERs at 35 degrees C and cannot evaluate efficiencies at other lower temperatures in majority zones. The right figure shows calculated full and half ERs and actual ER and operating hours at each outdoor temperature. When the outdoor temperature decreases from 35 degrees C, cooling load decreases and both full and half ERs increase by same reason as for fixed capacity unit. The inverter unit changed capacity between full and half capacity without on-off, and actual ER increases from full ER at 35 degrees C to half ER at about 28 degrees C. When cooling load becomes smaller than the half capacity, the unit enters on-off operation and actual ER decreases from half ER. Cspf is a kind of weighted average of actual ER for all operating temperatures. Cspf can evaluate higher efficiency of the inverter unit, which can change capacity without on-off, as well as higher efficiency at lower outdoor temperatures. Next, please. ISO 16358-1 specifies reference load and hours. Cspf of T1 climate means calculated value in these conditions. The upper figure shows ISO T1 load at each outdoor temperature Tj. ISO load is calculated by a straight line connecting full capacity of the product at 35 degrees C and 0 at 20 degrees C. ISO load is equal to full capacity over 35 degrees C, based on the assumption that both fixed and variable capacity units cannot increase capacity more than full capacity. The middle figure shows ISO T1 bin hours NJ at each outdoor temperature TJ. The total of ISO T1 hours is 1,817 hours. Total hours TH can be selected considering daily operating hours of air conditioners. The lower figure shows an example of hours whose distribution of fractions is same as ISO T1 hours, but the total is 2,920 hours, which correspond to 8 hours per day. Fraction of hours is bin hours divided by total hours at each outdoor temperature. Cspf becomes same when the fractions of hours are same. This is because Cspf is a kind of weighted average of actual ER for all operating outdoor temperature, and the weight factor at each outdoor temperature is determined by load and fractions of hours. Next, please. This page shows calculation example of ISO T1 load for the case of 35 degrees C full capacity 2.8 kilowatt. The figures in this page are same as upper and middle figures in the previous page. The equation of a straight line connecting full capacity at 35 degrees C and 0 at 20 degrees C is expressed as 35 degrees C full capacity multiplied by a function of outdoor temperature Tj. When 35 degrees C full capacity is 2.8 kilowatt, the equation becomes the next line. From this equation, load at outdoor temperature 29 degrees C becomes 1.680 kilowatt, and load at 25 degrees C becomes 0.933 kilowatt. In the lower figure, ISO T1 bin hours exist from 21 to 35 degrees C. Because load at each TJ is expressed as 35 degrees C full capacity multiplied by function of outdoor temperature TJ, load at each TJ from 21 to 35 degrees C can be calculated by this equation. Next, please. This page shows test points for fixed and variable capacity unit. This table is partial quotation from the ISO standard, and each row from the left shows kind of test, measured characteristics in the test, type of product, fixed and variable capacity unit, and default values to calculate the 29 degrees C value. Test points are shown by black squares in the rows of the products. Test points for fixed capacity unit are full capacity of 35 and 29 degrees C. Test points for variable capacity unit are full and half capacities at 35 degrees C. For variable capacity unit, full capacity and input at 29 degrees C are calculated from 35 degrees C values multiplied by the default value in the right-hand row of the table. Almost all Asian countries, including ASEAN, calculate 29 degrees C capacity and input of fixed capacity unit using the same default to reduce the test points, as shown in the bottom line of the table. This is reasonable because the difference by this test is small enough compared to the difference between fixed and variable capacity unit. All calculation examples in this presentation are based on using these defaults. Next, please. This page shows cooling capacity and input at temperatures other than 35 degrees C. The left figures show full capacity and input at each outdoor temperature Tj for fixed capacity unit, and the right figures show full and half capacities and inputs at each Tj for variable capacity unit. Respective capacities and inputs at 29 degrees C are calculated from 35 degrees C values multiplied by the defaults shown in the figure. Capacities and inputs at other temperatures are shown by straight lines connecting the values at 35 and 29 degrees C. Accordingly, full and half capacities and inputs can be calculated from 35 degrees C values multiplied by functions determined by Tj. Although ER is not shown in the figures, ER at each Tj can be calculated from the capacity divided by the input at each Tj. Next, please. This page shows calculation example of full and half capacities and inputs for variable capacity unit. In the case of 35 degrees C full capacity 2.8, full input 0.95, half capacity 1.4, and half input 0.37 kilowatt. The equations for full capacity and input in this page are applicable to fixed capacity unit when the defaults are used to calculate 29 degrees C values. The figures in this page are same as the figures for variable capacity unit in the previous page. Using the default for 29 degrees C, 29 degrees C full capacity is 35 degrees C full capacity 2.8 kilowatt multiplied by default 1.077 equal to 3.016 kilowatt. 29 degrees C half capacity is 35 degrees C half capacity 1.4 kilowatt multiplied by 1.077 equal to 1.508 kilowatt. 29 full input is 35 degrees C full input 0.95 kilowatt multiplied by default 0.914 equal to 0.868 kilowatt, and 29 degrees C half input is 35 degrees C half input 0.37 kilowatt multiplied by 0.914 equals to 0.338 kilowatt. At outdoor temperature 25 degrees C, the equation of the straight line connecting 35 and 29 degrees C is expressed as shown. Using this equation, 25 degrees C full capacity becomes 3.160 kilowatt. In the same way, 20 degrees C half capacity becomes 1.580 kilowatt. 25 degrees C full input becomes 0.816 0.13 kilowatt, and 25 degrees C half input become 0.317 kilowatt. Because 29 degrees C full capacity in the equation of the straight line is 35 degrees C full capacity multiplied by default 1.077, the equation can be expressed as 35 degrees C full capacity multiplied by a function of outdoor temperature Tj, which is 25 degrees C in this case. In the same way, half capacity, full input, and half input at each Tj can be expressed as 35 degrees C value multiplied by function determined by only Tj. Accordingly, full and half EERs at each Tj also can be expressed as 35 degrees C value multiplied by function determined only by Tj. ISO T1 bin hours exists from 21 to 35 degrees C. Full and half capacity inputs and EERs at each Tj from 21 to 35 degrees C can be calculated only from 35 degrees C value and outdoor temperature Tj. Next, please. This page shows actual EER at each outdoor temperature for fixed and variable capacity unit. The upper left figure shows load and full capacity, and the lower left figure shows full and actual EER for fixed capacity unit at each outdoor temperature. For fixed capacity unit, load is lower than full capacity under 35 degrees C, and the unit enters on-off operation in this zone. Actual EER decreases from full EER by on-off. Amount of reduction is 0 at 35 degrees C and 25% when load is 0 at 20 degrees C. This 25% is according to the default of degradation coefficient 0.25 specified in the ISO standard. The upper right figure shows load and full and half capacities, and the lower right figures show full, half, and actual EER for variable capacity unit at each outdoor temperature. Variable capacity units change capacity between 35 degrees C and the cross temperature of load and half capacity Tc. Actual EER does not decrease when the unit continuously operates and increases from full EER at 35 degrees C to half EER at Tc in this zone. It is assumed that variable capacity unit enters on-off operation under half capacity. Then actual EER decreases from half EER under the cross temperature Tc. Amount of reduction is 0 at Tc and 25% when load is 0 at 20 degrees C. Because reduction starts from half EER, which is much higher than full EER. Actual EER for variable capacity unit after reduction is also much higher than for fixed capacity unit. Next, please. This page shows calculation example of actual EER for fixed capacity unit in the case of 35 degrees C full capacity 2.8 and full input 0.95 kilowatt. Actual EER in on-off zone can be calculated by the equation shown here. The equation shows that actual ER at each outdoor temperature Tj is full ER multiplied by a reduction factor determined by load divided by full capacity, because both load and full capacity at each Tj can be expressed as 35 degrees C full capacity multiplied by function of only Tj. The reduction factor in the equation is determined only by Tj. The upper and middle figures in this page are same as the figures for fixed capacity unit in the previous page. And the lower figure shows full and actual input at each Tj, referring to the example of cooling capacity and input in the previous page. 29 degrees C full ER is full capacity 3.016 kilowatt divided by full input 0.868 kilowatt equal to 3.475. From the equation in this page, 29 degrees C actual ER becomes 3.090. Actual input is load divided by actual ER. Referring to the example of ISO T1 load in the previous page, 29 degrees C actual input is load 1.680 kilowatt divided by actual ER 3.090 equals to 0.544 kilowatt. Because full ER in the equation of actual ER is 35 degrees C full ER multiplied by function of only Tj. Actual ER can be also expressed as 35 degrees C full ER multiplied by a function of only Tj. Then actual input, which is load divided by actual ER, can be expressed as 35 degrees C full capacity divided by 35 degrees C full ER multiplied by a function of only Tj. ISO T1 bin hours exists from 21 to 35 degrees C. Actual ER and actual input at each Tj from 21 to 35 degrees C can be calculated in this way. Next, please. This page shows calculation example of the cross temperature Tc of load and half capacity in the case of 35 degrees C full capacity 2.8, full input 0.95, half capacity 1.4, and half input 0.37 kilowatt. From the equation for the cross point of two straight lines for ISO T1 load and cooling half capacity, cross temperature Tc becomes the equation shown here. CRH is in this equation is 35 degrees C half capacity divided by 35 degrees C full capacity, which is 1.4 kilowatt divided by 2.8 kilowatt equal to 0.5 for this example. The upper and middle figures in this page are same as the figures for variable capacity unit in the previous page. The lower figure shows full, half, and actual input at each outdoor temperature Tj. By entering CRH 0.5 in the equation, the cross temperature Tc for this example becomes 28.16 degrees C. Referring to the equation in the example of cooling half capacity and input in the previous page, half capacity at Tc becomes 523 kilowatt, and half input at TC become 0.334 kilowatt. Half ER at TC is half capacity 1.523 kilowatt divided by half input 0.334 kilowatt equal to 4.560. Next, please. Okay. This page shows a calculation example of actual ER for the same case as previous page. Actual ER in capacity changing zone is expressed in the equation here, which correspond to a straight line connecting full ER at 35 degrees C and half ER at the cross temperature TC. The figures in this page are same as in the previous page. Referring to the example in the previous page, 35 degrees C full ER is full capacity 2.8 kilowatt divided by full input 0.95 kilowatt equal to 2.947. The cross temperature TC is 28.16 degrees C, and half ER at TC is 4.560. From the equation in this page, 29 degrees C actual ER becomes 4.362. Referring to the example of ISO T1 load, 29 degrees C actual input is load 1.680 kilowatt divided by actual ER 4.362 equal to 0.358 kilowatt. ISO T1 beam hours exists from 21 to 35 degrees C. Actual ER and actual input at each TJ in capacity changing zone from the cross temperature TC to 35 degrees C can be calculated in the same way, which is from 29 to 35 degrees C in this example. In order to calculate the actual ER of variable capacity unit in capacity changing zone, 35 degrees C half capacity and ER data are required, as well as 35 degrees C full capacity and ER data. Next, please. This page shows calculation example of actual ER in on-off zone of variable capacity unit for the same example as in the previous page. Actual ER in on-off zone can be calculated by this equation here. It is similar to the equation in on-off zone of fixed capacity unit, but actual ER in this page is half ER at each TJ multiplied by a reduction factor, which is a function of load divided by half capacity. This means that reduction starts from half ER. The figures in this page are same as those in the previous page. Referring to the example of half capacity and input in the previous page, 25 degrees C half ER is half capacity 1.580 kilowatt divided by half input 0.317 kilowatt equal to 4.984. From the equation in this page, 25 degrees C actual ER becomes 4.474. Referring to the example of ISO T1 load in the previous page, 25 degrees C actual input become load 0.933 kilowatt divided by actual ER 4.474 equal to 0.209 kilowatt. ISO T1 bin hours exists from 21 to 35 degrees C. Actual ER and actual input at each TJ in on-off zone from 21 degrees C to the cross temperature TC can be calculated in the same way, which is from 21 to 28 degrees C in this example. In order to calculate actual ER of variable capacity unit in on-off zone, 35 degrees C half capacity and ER data are required, as well as 35 degrees C full capacity and ER data. Next, please. Okay, this page shows calculation of CSTL, CSEC, and CSPF. Cooling seasonal total load CSTL is sum of load at each outdoor temperature TJ multiplied by bin hours NJ. Cooling seasonal energy consumption CSEC is sum of actual input at each TJ multiplied by bin hours NJ. Cooling seasonal performance factor CSPF is total load CSTL divided by total energy consumption CSEC. CSPF is a kind of weighted average of actual EER for all operating temperatures from 21 to 35 degrees C. The upper figure in this page shows load and actual input at each TJ. The middle figure shows actual EER, and the lower figure shows ISO T1 bin hours NJ at each TJ. When temperature hours is determined, total load CSTL becomes 35 degrees C full capacity in watts multiplied by a constant. As shown in the example of ISO T1 load in the previous page, load at each TJ can be calculated from 35 degrees C full capacity multiplied by a function determined only by TJ. Because CSTL is sum of load multiplied by bin hours NJ at each TJ, it becomes 35 degrees C full capacity multiplied by a function of only TJ and NJ. When bin hours NJ at each TJ is determined, this value becomes a constant. The constant is 0.7331 kilowatt hour per watts for ISO T1 temperature hours. The reason we use watts for capacity in the easy equation here is that ISO calculation tool is indicating to enter capacities and inputs in watts. Explanation about the calculation tool will be shown later. Next, please. CSTL is sum of load multiplied by hours for all operating temperatures. This page shows calculation example for 35 degrees C full capacity 2.8 kilowatt and ISO T1 bin hours. In this table, the first line shows outdoor temperature TJ. The second line shows ISO T1 bin hours NJ at each TJ. And total of this line in the lower right end row becomes 1,817 hours, which was shown in the figures of ISO T1 hours in the previous page. The third line shows cooling load at each TJ, which can be calculated as shown in the example of ISO T1 load in the previous page. The fourth line shows cooling load in the third line multiplied by bin hours in the second line. And total of this line becomes cooling seasonal total load, CSTL. From this table, CSTL is 2053 kilowatt hour as shown in the lower right-hand row. On the other hand, according to the easy equation of CSTL in the previous page, CSTL is 35 degrees C full capacity 2,800 watts multiplied by constant 0.7331, which also equals to 2053 kilowatt hour. When the total hour TH is different from 1,817 hours and is 2,920 hours, CSTL is multiplied by 2,920 over 1,817 equals 3,299 kilowatt hour. Next, please. This page shows an easy equation of Cspf and Csec for fixed capacity unit. When temperature hours is determined and 29 degrees C full capacity and input are calculated by default, Cspf of fixed capacity unit can be calculated from 35 degrees C full EER multiplied by a constant. Cspf is sum of load, CSTL, divided by sum of actual input, CSEC. As shown in the previous page, CSTL is 35 degrees C full capacity multiplied by a constant. CSEC is sum of actual input. It is sum of load divided by actual ER and becomes 35 degrees C full ER divided by full capacity divided by 35 degrees C full ER multiplied by a function of only TJ and bin hours NJ. The function becomes constant when bin hours NJ at each TJ is determined. Accordingly, CSPF, which is CSTL divided by CSEC, becomes 35 degrees C full ER multiplied by a constant. For the case of ISO T1 temperature hours, this constant is 1.062. From the easy equations of CSTL and CSPF, CSEC becomes 35 degrees C full capacity in watts multiplied by 0.7331 divided by 35 degrees C full EER multiplied by 1.062. In the case of cooling only climate, CSEC becomes annual energy consumption. When the total hours TH is different from 1,817 hours, CSEC is multiplied by TH over 1,817. Next, please. CSEC is sum of actual input multiplied by hours for all operating temperatures. This page shows calculation example of fixed capacity unit for 35 degrees C full capacity 2.8 and full input 0.95 kilowatt and ISO T1 bin hours. In this table, the first line shows outdoor temperature TJ. The second line shows ISO T1 bin hours NJ at each TJ. The third line shows actual input at each TJ, which can be calculated as shown in the example of actual ER for fixed capacity unit. The fourth line shows the actual input in the third line multiplied by bin hours NJ in the second line, and total of this line becomes cooling seasonal energy consumption, CSEC. From this table, CSEC is 655.9 kilowatt hour, as shown in the lower right-hand row. Referring to the CSTL table in the previous page, cooling seasonal total load, CSTL, for this example is 2053 kilowatt hour. Cooling seasonal performance factor, Cspf, is CSTL 2053 kilowatt hour divided by CSEC 655.9 kilowatt hour equal to 3.13. On the other hand, according to the easy equation in the previous page, CSPF is 35 degrees C full EER multiplied by 1.062. Referring to the example data, 35 degrees C full EER is full capacity 2.8 kilowatt divided by full input 0.95 kilowatt equal to 2.947, and CSPF is 2.947 multiplied by 1.062 equal to 3.13. Cooling seasonal total load from the easy equation in the previous page is full capacity 2,800 watts multiplied by 0.7331 equal to 2,053 kilowatt hour, and CSEC becomes CSTL 2,053 kilowatt hour divided by CSPF 3.13 equal to 655.9 kilowatt hour, which is same to the result of this table. When the total hour TH is different from 1,817 hours and is 2,920 hours, CSEC is multiplied by 2,920 over 1,817 equal to 1,054 kilowatt hour. Next, please. This page shows the equation of CSPF for variable capacity unit with similar style to the easy equation for fixed capacity unit. For variable capacity unit, the multiplier in the equation is not constant and becomes a function of half capacity ratio CRH and half ER ratio ERH. CRH is 35 degrees C half capacity divided by 35 degrees C full capacity, and ERH is 35 degrees C half ER divided by 35 degrees C full ER. In calculation of the cross temperature TC, half capacity ratio CRH is required. Half ER ratio ERH is also required to calculate actual ER at each TJ for both capacity changing zone and on-off zone. Calculation tool is attached to ISO standard 16358-1, Amendment 1, 2019. Cooling seasonal energy consumption, CSEC, can be calculated from CSTL by the easy equation shown here, divided by the result of the calculation tool, or directly can be calculated by the calculation tool. In the case of cooling-only climate, CSEC becomes annual energy consumption. When the total hours TH is different from 1,817 hours, CSEC is multiplied by TH over 1,817. Next, please. This page shows calculation example of CSEC and Cspf for 35 degrees C full capacity 2.8, full input 0.95, half capacity 1.4, and half input 0.37 kilowatt, and ISO T1 bin hours. In this table, the first line shows outdoor temperature TJ. The second line shows ISO T1 bin hours at each TJ. The third line shows actual input at each TJ, which can be calculated as shown in the example of actual EAR for variable capacity unit. The fourth line shows the actual input in the third line multiplied by bin hours in the second line. And the total of this line becomes cooling seasonal energy consumption CSEC. From this table, CSEC is 476.7 kilowatt hour as shown in the lower right-hand row. Referring to the CSTL table in the previous page, cooling seasonal total load CSTL for this example is 2,053 kilowatt hour. Cspf is CSTL 2,053 kilowatt hour divided by CSEC 476.7 kilowatt hour equal to 4.31. There is no easy equation of variable capacity unit. When total hour TH is different from 1,817 hours and is 2,920 hours, CSEC is multiplied by 2,920 over 1,817 equal to 766.1 kilowatt hour. Next, please. Okay, this page shows the procedure to download ISO calculation tool. The calculation tool is attached to ISO standard 16358-1, Amendment 1, 2019. The standard can be purchased from the website shown here. Price is 118 Swiss franc, which is about 133 US dollars as of January 2021. Please note that this standard and the calculation tool are copyrighted by ISO. Technical committee of each country may purchase the standard and share within the committee member for the purpose of developing the national standard. When the standard is purchased, the Excel tool file is shown on the download page, as well as PDF of the amendment of the standard. Next, please. This page shows the sheet for variable capacity unit in the calculation tool file. This sheet can be selected from the bottom of the Excel sheet. The upper portion of this sheet is for Cspf of ISO T1 climate, which is usually used in the world except for the Middle East. The lower portion is for Cspf of ISO T3 climate, which is based on the temperature of UAE and Saudi Arabia in the Middle East. In the upper portion of the sheet, required test only at the upper right corner should be selected. Full and half capacities and powers are shown in the upper right table. When these data are changed to any optional values, CSTL, CSEC, and CSPF in the middle table will automatically change to the calculated values. The capacities and powers shall be entered in watts and calculated. CSTL and CSEC are expressed in kilowatt hour. There is another sheet for fixed capacity unit, which can be selected from the bottom of the sheet, but it is easier for fixed capacity unit to use the easy equation in the previous page. Next, please. This page shows an example of calculation by the ISO calculation tool. First, variable capacity unit sheet in the previous page is selected at the bottom of the Excel sheet. Next, in the upper portion for CSPF P1 calculation, required test only is selected from the test item at the upper right corner. Another selection with optional test is selected only when the minimum capacity is tested. The minimum capacity is usually not tested for room air conditioners because it is difficult for laboratories to measure the small capacity within the limit of uncertainty specified in the ISO standard 16358-1. Next, as an example, full capacity 2,800, full power 950, half capacity 1,400, and half power 370 in watts are entered in the standard condition 35°C table at the upper left corner. Then CSTL 2053 and CSEC 477 in kilowatt hour and CSPF 4.31 are automatically shown in both the international and custom rows of the middle table. Because this example is in ISO T1 condition, the data for international and custom rows are the same. When results in other conditions are required, the data sheet should be selected in advance from the bottom of the Excel sheet, and corresponding bin hours should be entered in the bin hour table. Then results for the entered temperature hours are shown in the custom row of the table. The calculated data and the calculated data are same as the calculation example in the previous page. When total hours TH is different from 1,817 hours, CSTL and CSEC in the middle table should be multiplied by TH over 1,817. Okay, we will have 15 minutes break here. Let's continue later. Thank you.
Thank you so much, Izushi-san, for the presentations. Now we will have 15 minutes break. Right now it's 10:15 in Jakarta time. So we will start in 10:30 Jakarta time. So please adjust it with your time as well. And we will have a break starting now. Thank you so much, everyone. And we will see you in 15 minutes.
Okay. Okay, let's continue the presentation. Characteristics of Cspf are explained from this page. Cspf of variable capacity units changed by half capacity ratio CRH and half ER ratio ERH. CRH is 35 degrees C half capacity divided by 35 degrees C full capacity, and ERH is 35 degrees C half ER divided by 35 degrees C full ER. This page shows effect of half ER ratio ERH on Cspf of variable capacity unit. The upper left figure in this page shows actual ER divided by 35 degrees C full ER at each outdoor temperature TJ for fixed capacity and variable capacity unit. 35 degrees C full ER is same for both fixed capacity and variable capacity examples here. Half capacity ratio CRH is 0.5 and half ER ratio ERH is 1.2 and 1.4 for variable capacity unit examples. The lower left figure shows ISO T1 bin hours at each TJ. The right figure shows Cspf divided by 35 degrees C full ER for fixed capacity unit and variable capacity unit with different half ER ratio ERH from 1.2 to 1.4, which is usual range in laboratory tests. Cspf divided by 35 degrees C full ER is a kind of weighted average of actual ER divided by 35 degrees C full ER. It is 1.062 for fixed capacity unit. Cspf divided by 35 degrees C full ER of variable capacity unit increases when half ER ratio ERH increases and varies from 1.376 to 1.592 in usual range of half ER ratio from 1.2 to 1.4. Cspf for variable capacity unit is 30 to 50% higher than for fixed capacity unit. Next, please. This page shows effect of half capacity ratio CRH on Cspf of variable capacity unit. ISO standard specifies that tested half capacity ratio CRH to full capacity shall be between 0.45 and 0.55. Usually, manufacturers have test modes to fix the inverter frequency for full and half capacity tests so that the capacity ratio becomes within this range. Laboratories request the information to set these modes at the time of certification test. The left figure shows load and half capacities divided by 35 degrees C full capacity at each outdoor temperature. The load divided by 35 degrees C full capacity is 1.0 at 35 degrees C. The example half capacities divided by 35 degrees C full capacity are 0.45, 0.5, and 0.55 at 35 degrees C. The right figure shows CSPF divided by 35 degrees C full ER for half capacity ratio CRH from 0.45 to 0.55. Half ER ratio ERH of the example are 1.2 and 1.4, which correspond to lower and upper sides of the usual range in laboratory tests. For both ERH 1.2 and 1.4, variation of CSPF by half capacity ratio CRH is within only 1%. CSPF practically does not change by half capacity ratio CRH in the ISO specified range from 0.45 to 0.55. CSPF of variable capacity unit is practically determined by 35 degrees C full ER and half ER ratio ERH. Next, please. This page shows comparison between WER or WCOP and CSPF. WER is calculated by the equation here, which is a weighted average of 40% full ER and 60% half ER tested at 35 degrees C. The upper left figures show full and half ER tested and calculate WER at 35 degrees C and actual ER calculated at each outdoor temperature, TJ. For this example, half capacity ratio CRH is 0.5 and half ER ratio ERH is 1.2. The lower left figure shows ISO T1 bin hours at each TJ. The right figures show calculated WER and CSPF divided by 35 degrees C full ER with different half ER ratio ERH from 1.2 to 1.4. WER is 12 to 24% higher than 35 degrees C full ER, but CSPF is 38 to 58% higher than 35 degrees C full ER in usual range of half ER ratio from 1.2 to 1.4. WER partially can evaluate higher efficiency of variable capacity unit, but it cannot evaluate higher efficiency at lower operating temperatures. Accordingly, seasonal or annual energy consumption cannot be directly calculated from WER. Next, please. This page shows effect of higher temperature hours on CSPF. The upper left figure shows ISO T1 bin hours and plus 2 degrees hours shifted to higher temperature side at each outdoor temperature TJ. The lower left figure shows actual ER divided by 35 degrees C full ER at each TJ for fixed capacity and variable capacity unit. These are same for the both hours. Half capacity ratio CRH and half ER ratio ERH of the example variable capacity unit are 0.5 and 1.2. Cspf decreases when temperature hours becomes higher because actual ER at higher temperature side is lower than at lower temperature side. The right figure shows Cspf divided by 35 degrees C full ER of ISO T1 and plus 2 degrees C shift hours for fixed capacity unit and variable capacity unit in usual range of half ER ratio from 1.2 to 1.4. Reduction of Cspf by plus 2 degrees shift is about 2% for fixed capacity unit and about 5% for variable capacity unit. However, the rank of product efficiency grade does not change by this temperature shift. ISO T1 Cspf can be effectively used for labeling purpose. Next, please. This page shows the case of 0A temperature hours proposed by U4E. The upper left figure shows 0A temperature hours with total 4,973 hours and ISO T1 fractions of hours with total 2,920 hours for comparison purpose, which correspond to 8 hours per day. The lower left figure shows actual ER divided by 35 degrees C full ER at each outdoor temperature for fixed capacity and variable capacity unit. These are same for the both hours. Half capacity ratio CRH and half ER ratio ERH for the example variable capacity unit are 0.5 and 1.2. The right figure shows Cspf divided by 35 degrees C full ER for ISO T1 fractions and U4E 0A temperature hours for fixed capacity unit and variable capacity unit in usual range of half ER ratio ERH from 1.2 to 1.4. Cspf for ISO T1 fractions of hours does not change by total hours. Cspf for U4E temperature hours is very close to the plus 2 degrees shift temperature hours in the previous page. And the rank of product efficiency grade does not change from ISO T1 fractions of hours. Total hours of U4E 0A 4,973 hours, which correspond to 13.6 hours per day, may be too long for usual use of air conditioners. Next, please. This page shows the load and hours for labeling of India. The upper left figure shows ISO T1 and Indian temperature hours. ISO T1 load is 0 at 20 degrees C, but the load of India is 0 at 23 degrees C. Temperature hours of India is higher than ISO T1, but total hours 1,600 is less than 1,817 of ISO T1 hours. The lower left figure shows actual EER divided by 35 degrees C full EER for fixed capacity and variable capacity unit. Half capacity ratio CRH and half ER ratio ERH of the example variable capacity unit are 0.5 and 1.2. When load zero temperature changed to 23 degrees C from 20 degrees C, actual ER becomes lower in the on-off zone for both fixed capacity and variable capacity unit. In addition, for variable capacity unit, gross temperature of load and half capacity becomes higher and on-off operation starts at a higher outdoor temperature. On the other hand, actual ER over 35 degrees C is equal to full ER, and same for fixed capacity and variable capacity units. The right figure shows Cspf divided by 35 degrees C full ER of ISO T1 and India for fixed capacity unit and variable capacity unit in usual range of half ER ratio from 1.2 to 1.4. Cspf of variable capacity unit for India is 20 to 30% higher than for fixed capacity unit. This is significantly lower than the case of ISO T1 climate. In the case of India, if a greater capacity unit is selected, which can increase capacity over 35 degrees C, energy saving effects of variable capacity unit becomes greater, like ISO T1 climate. But size and price of the air conditioner also increases. For example, ISO T3 climate is rated at 46 degrees C outdoor temperature. When outdoor temperature increases from 35 degrees C to 46 degrees C, cooling capacity of air conditioners decreases 14%, but required cooling load increases 73%. This means the air conditioner rated in ISO T3 condition at 46 degrees C needs about double capacity compared to ISO T1 condition. Next, please. The figure in this page shows comparison of cooling seasonal energy consumption CSEC for ISO T1 fractions with total 1,817, 2,920, and 4,380 hours, U4E 0A hours with total 4,973 hours, and Indian hours with total 1,600 hours. Each total hours correspond to 5.0, 8.0, 12.0, 13.6, and 4.4 hours per day. Example case is for variable capacity unit with 35 full degrees C full capacity 2.8, full input 0.95, half capacity 1.4, and half input 0.37 kilowatt. Seasonal or annual energy consumption changed by total hours and fractions of hours. As shown in this figure, total hours has a big impact on estimation of energy consumption. Energy saving is estimated based on the annual energy consumption and total number of air conditioners in the field. It is necessary to select the total hours carefully. Next, please. From this page, general procedure to make labeling table is explained. This page shows purpose of MEPS and labeling. Minimum energy performance standard MEPS is set to limit the lowest energy efficiency level of products in order to avoid lower efficient products sold in the market. Energy label is shown on the products to promote higher efficient products recognized and selected by consumers, and to promote higher efficient products developed by manufacturers. Combination of MEPS and labeling is very important to give a choice of selection to consumers. Consumers usually select products from price and efficiency, but some people certainly need cooling itself during hot season. The efficiency of lower price units should be increased step by step. Usually, 5-star label showing higher efficient products by greater number of stars is used, and star 1 is usually set to be equal to MEPS. Next, please. The figure in this page shows an example of Cspf distribution in the recommended policy roadmap presented in the work package 2 by IIEC. The data show efficiencies converted to ISO T1 Cspf for products under 25 kilowatt cooling capacity sold in the markets in Indonesia, Malaysia, Thailand, and Singapore. Dark circles show inverter models and light circles show fixed speed models. As shown in the figure, Cspf of inverter models are distributed in the higher range from 4 to 8, and Cspf of fixed speed models are distributed in the lower range from 3 to 5. Next, please. The table in this page also shows distribution from the same example as in the previous page, but shows the products under 4.5 kilowatt cooling capacity. The first line shows different categories of efficiency level. Next to the left-hand row shows 2020 harmonized MEPS level for ASEAN, which is Cspf 3.08. Next 3 rows show higher Cspf levels 3.7, 4.6, and 6.09, corresponding to 20, 50, and 98% higher levels than 3.08. The second line shows number of models with Cspf higher than the specified levels in the first line. The third line shows percent value of the number in the second line divided by the total number of products, 2,134, under 4.5 kilowatt cooling capacity. From this data, 2% of products are under Cspf 3.08, 22% are under Cspf 3.7, 50% are under Cspf 4.6, and 90% are under Cspf 6.09. in the current mixed market of Indonesia, Malaysia, Thailand, and Singapore. Contribution of each country is unknown from these data. For the actual investigation for the labeling, each country should use the data for its own market. Next, please. This page shows setting procedure of star 1 corresponding to MEPS and highest star 5 of labeling table. The CSPF distribution in the previous page is used here for an example. For the actual investigation, each country should prepare the table of its own market first through preliminary registration for suppliers and products. Usually, star 1 level is set to cut off lower efficient models from 10 to 20% at maximum, which corresponds to 3.3 to 3.6 in this example, because 22% products are under 3.7 in the previous page. Star 5 level is usually set to cover higher efficient models from 10 to 20%, which corresponds to 5.6 to 6.1 in this example, because 10% of products are over 6.09 in the previous page. Star 2 to star 4 levels are selected to fill the gap between star 1 and star 5, which corresponds to 3.8 to 4.1 for star 2, 4.3 to 4.7 for star 3, and 4.9 to 5.3 for star 4 for this example. Next, please. This page shows study of proposed MEPS 3.7 in the recommended policy roadmap. Proposed MEPS 3.7 in 2023 might be or might not be accepted in the stakeholders meeting in each country, because more than 20% products are currently under this level. It may be challenging for the countries with local manufacturers, because local manufacturers sometimes have to leave the market by too high MEPS level. It should be noted again that this distribution is mixed data of Indonesia, Malaysia, Thailand, and Singapore. In some countries, more than 22% of products may be currently under Cspf 3.7. Each country should evaluate the MEPS level based on Cspf distribution in its own market, requests for lower price products from consumers, and development policy of local manufacturers. Next, please. This page shows general procedure for renewal of the labeling table. For renewal of the labeling table, at least 3 to 4 years may be required, because in addition to the period to develop higher efficient models, manufacturers need some period to sell the products in the market to return the investment. The period and amount of investment for the new products may be different by increasing amount of efficiency. In the new table, efficiency levels are usually 1 grade higher than in the previous table. If new levels are too high, star rank may drop, after development for some manufacturers, which will discourage manufacturers a lot. The table in this page shows an example of new table. New star 1, 2, 3, and 4 levels are same as the old star 2, 3, 4, and 5 levels in the previous page. New star 5 level 6.3 to 6.9 is set to higher level than before, as an example. Of course, CSPF distribution at the time of renewal should be evaluated again before determining new efficiency levels. Next, please. This page shows current and new labeling table of India. The table shows star 1 to 5 levels of old 2018 label and new 2022 label. Values are based on ISER, which is Indian CSPF, shown in the example of Indian laws and hours in the previous page. The bracket data in the star 1 law are converted value to ISO T1 CSPF based on the calculation for fixed capacity unit. The bracket data in the star 5 law are converted value to ISO T1 CSPF based on the calculation for variable capacity unit. Star 1 level 3.3 and star 2 level 3.5 in the new 2022 label are same as the star 2 and star 3 levels in the old 2018 label. Star 3 level 3.8 and star 4 level 4.4 in the new 2022 label are a little lower than star 4 level 4.0 and star 5 level 4.5 in the old 2018 label. This may be based on the current CSPF distribution in the Indian market. Star 5 level 5.0 in the new 2022 label is newly set at higher level. Next, please. Okay, this page shows summary. Advantage of CSPF to conventional ER and WER were explained. Calculation method of load and product performances, as well as examples, were explained. Calculation method of CSTL, CSEC, and CSPF, as well as examples, were explained. Characteristics of CSPF and CSEC were explained. General procedure to make labeling table and renewal were explained. This is the end of the presentation. Thank you.
Thank you so much, Minato-san, for the presentations. So we would like to invite everyone, if they have any questions for the presentations previously, please feel free to write it down or please raise your hand. And while waiting, I'll just gonna announce that this presentations later could be shared, and later on the informations on this, the recording will be shared as well to you, so that you and perhaps your colleague could actually run through these sessions again. So is there anyone who would like to ask a question? Okay. So I guess we need to at least give the opportunity and wait for the questions. Susan, if you are okay with that. Is there anyone would like to ask, perhaps from the Singapore delegates, Myanmar delegates would like to ask question for this lecturing? Okay, so this is the question from Pei Chen Eng. Is Cspf applicable for multi-split aircons as well? Minute Suisan.
Multi-split aircon, yes, it's applicable, but the temperature condition and load condition will be different because usage basically for building load is different from house load. So the load condition and the temperature distribution will be different.
Okay, thank you so much, Minute Suisan. So I hope that answers your question, Mr. Pei Chen Ang. May we have other questions, or if Mr. Pei Chen Ang have additional question or follow-up question, we are actually welcome. So I guess we can wait for a couple of minutes until 11:10. If there are no more questions, then we could proceed with the closing. Is that okay, Mr. Minete Sisan?
Okay, no problem.
Yeah. Or perhaps from ACE, if you have any questions as well, you can raise it here.
We can.
It's also possible, yeah, in the session, if we have several questions that maybe after the this event, and some yeah, we need more understanding in this yeah, this lecture. Hopefully we could also send you an email that will be collected by ACE, and of course hopefully you will be happy to answer the queries to improve our understanding to Cspf. And of course, it's very challenging for, especially for countries that we haven't got the facilities or laboratories to test the AC and also apply this Cspf. So we also hope that the countries today that doesn't have the facility, perhaps in the near future, we also could build the testing laboratories in your countries. So in the future, furthermore, we also could have like several regional activities and also standard, and also what we have maybe the mutual commissions agreement or MRA for this AC. So the barrier of the trading, and also for the yeah, of course, applications of the AC in each country in region will be easier. Yeah, I think so. Yeah, Mr. Izuzi. Yeah.
Yes, of course. I will welcome questions by email. Anytime we will answer about that.
Sure. So I guess from Myanmar, there is no question, as it confirms by Ms. Wei. So I guess we will directly pass the floor to Dr. Andy for closing remarks and to end this session. And just to remind everyone that this will be available as well. And if you are have follow-up questions after our sessions, I think Jiraya side and A side will assist you accordingly to this regard. So Dr. Andy, please.
Yeah, thank you, Amira, and also Izushi-san for your kindly and also patiently lecture for us about the CSPF. And we hope that by these online sessions, yeah, still unfortunately we couldn't meet face to face. And of course, hopefully, with this opportunity and this platform, even though it's still online, but everybody could, I mean, more people could reach this lecture through online, through our YouTube channel. So the understanding of people in each country, not only maybe in region, but also globally, for the CSPF could be better. So again, I thank you so much for your support, your time, and also your participations in this meeting for all IMS from, especially from 5 countries, to support these activities, and also for the ACE colleague to provide this online lecturing. Thank you so much. Back to you, Amira.
Yes, so thank you so much, Dr. Andy. And that would be the end of our session. And we would like to highly appreciate all of the GRIA staff, as well as ACE, and then all of the participants from the 5 different countries of non-lab AMS, so that this will be a fruitful session for you, and hopefully later on we would have another meeting soon. So, and stay safe and healthy, and I would like to close this session right now. Thank you so much, everyone. Bye-bye.
Thank you.